We flew to 60,000 feet, as high as our planes could get. Once up there, we deployed the fuel lines and pumped the aerosols into the air, mostly sulfur dioxide and some other chemicals. It was a mix designed to stay up there and reflect sunlight back into space. Day after day, for 7 months, we flew those missions. After that, no more deadly heat waves.
Is what we just heard science fiction? I'm afraid no. It is literally reality. The clock is ticking, and the race to limit global warming is on. Why am I saying that? I'm saying that because last year, global average temperature came in at 1.48 degrees above pre-industrial. And that broke many records. That was clearly the warmest year since we are recording temperatures. Presumably, it was also the warmest year in the last 100,000 years. And there's the thing, only a small share, less than 5% of the heat hitting on the planet is actually trapped in the atmosphere. The lion's share of the heat hitting on the planet is actually captured in the oceans. And same picture there. In 2023 and 2024, surface water temperatures of oceans have been breaking all previous records. Now, those facts are very, very hard to digest. But they're good news. And the good news being that there's a very clear recipe on how we can limit global warming to the 1.5 limit. It's essentially 5 components, where the first component is a carbon budget for fossil fuels. We must not emit more than 250 gigatons of CO2 or greenhouse gases to the atmosphere. And the means to achieving that are very clear: massive emission reductions and phasing out fossil fuels, as has been concluded in the last COP conference. Now, the second component concerns the entire food system, currently emitting roughly 4 gigatons with some volatility. And this system has to go through a massive change to essentially take 5 gigatons annually from the atmosphere. Then components 3 and 4 are natural components. The entire biosphere we have on Earth, as well as the oceans, each of them removing net roughly 10 to 11 gigatons per annum from the atmosphere. And the fifth component is carbon removal, which has to scale to 5 to 10 gigatons within the next 25 years. Now, the likelihood that the recipe will look exactly like that in 2050 is low. Maybe the food system will take longer to transition, and the emissions need to be addressed and overcompensated by other components, for example, the nature components or carbon removal, or vice versa. Maybe we are slow and others need to help us. But I think all in all, this budget gives us a very, very good idea of what is allowed and not allowed to achieve climate targets. And very importantly, none of the lines shown here will do it on their own, only if all of them work together. Now, clearly, those numbers are also challenging figures. But what I personally find very inspiring, that with fast and strong actions, those numbers are achievable. And this is where I personally get a lot of energy from. And this is essentially what inspired and motivated the creation of Climeworks some 15 years ago. Now, 15 years back, 2009, when Jan and I started the journey, we were capturing CO2 on a couple of milligrams level. And interestingly, 2009 was also a record year. Global temperatures came in at 0.56 degrees. By then, that was the warmest year since temperatures have been recorded. Fast forward 5 years, in 2014, we released our first product. We call that a DAC 1. On the ton scale, and again, interestingly, take a guess, yet another record year. The warmest year on record by that time, 0.8 degrees. Only a year later, 196 nations signed the Paris Accord, claiming to limit global warming at 1.5 degrees Celsius. Yet another record year at 0.9 degrees Celsius. 2017, we started our first commercial plant on the scale of hundreds of tons of CO2 from the air. And what we saw is that the long-term warming trend continued. In 2021, we started the world's first plant capturing CO2 from the air and storing it in the ground in Iceland, Orca. Yet another year of continued warming globally. 2023, presumably the hottest year in the last 100,000 years. And exactly that was the year when we went through the construction phase of our scaled facility in Iceland that we call Mammoth. And exactly this facility started operation just a couple of weeks back, and it's operating on a scale of tens of thousands of tons per annum. And I'm afraid also this year we are on perfect track to again break records. In the first month of this year, global warming so far has been 1.6 degrees. Now, the last 15 years, obviously, have been a massive journey, both for global warming as well as for Climeworks. But we remain committed. We at Climeworks remain committed to continue to lead the race. At the end of the day, at Climeworks, we have 500 people out of 8 billion globally, and we commit to scaling carbon removal to gigaton in order to eventually have a chance to alter history. Exactly this is the goal of today. Today, we want to evaluate, explore together with you, and take you on a journey of talking about the 5 key success factors for making carbon dioxide removal a gigaton game. And we'll have a special deep dive on technology. But let's start with where everything begins. Everything begins with underground storage of CO2. If we don't have a chance to store CO2 in the ground, carbon removal will not happen. And we ask very often, is there enough space to store CO2 in the ground? The answer is yes. Globally, more than 9 billion tons of underground storage volume have been explored. Hotspots are in North America, in Northern European countries, Middle East and Africa, Japan, Australia. And in most of those regions, we are having project development activities ongoing so that we can scale globally. A second key success factor for carbon removal is energy. We at Climeworks commit to using renewable power or other forms of low-carbon energy to power our plants. Now, the beauty of air capture is that we can put our plants exactly where those forms of energy are available. And that is crucial, because air capture is an energy game. And to emphasize that with a couple of figures, a plant capturing 1 million tons of CO2 from the atmosphere per year will require somewhere between 300 to 500 megawatts. And interestingly, that's a small and big figure at the same time. Now, there's an interesting comparison I can offer you. In 2022, data centers globally consumed 65 gigawatts of power. This number is supposed to go up to 130 gigawatts in 2026, so in 2 years from now. Assume all of this power wasn't used for data centers, but for carbon removal. The respective platform that is created is somewhere in the range of 400 to 500 millions of tons of CO2 taken from the air per annum. That's presumably a scale our industry will achieve in 2040, so in 15 years down the road. Now, clearly, on the short term, there will be heavy competition for this energy. However, what makes me very confident and positive about this development is that the order of magnitude size of this problem is currently solved by another industry in a very agile way, in such that I'm super confident we can source similar quantities in 15 years down the road. A third component, cost, maybe the one that is mostly talked about. Well, it's decently complex to talk about cost, because cost is composed of different factors. There's the cost of capture. On top of that, there's some site-specific cost as well as company-specific cost. And presumably, the cost of capture, is what in our community typically is referred to as cost. So let's stick to that. With the current technology and scale we're operating in Iceland, we are rather closer to $1,000 than $100. We have very concrete plans to bring that to $250 to $350 by 2030, and to $75 to $150 by the year 2050. Now, interestingly, I very often, and throughout the last 17 years, very number of times heard, unless you reach $100, you won't be successful, or this is the range when air capture becomes affordable. I see that in a differentiated way of view. So I think the right benchmark, the right cost benchmark for air capture and carbon removal is actually the social cost of carbon, meaning what is the cost that society has to bear by emitting an additional ton of CO2? And just recently, a very renowned study came out showing that the social cost of carbon is slightly north of $1,000. So what that means is that already with technology we're having today, it is more economical to humanity to operate our plants than not operate them. And that's a massive, massive finding. And that's only the beginning, because we're further scaling, we're further developing our technology, and by that, we're reducing our cost and render it more economical. And there's no one better to talk about the technology development of direct air capture than my co-founder, Jan. Jan, please join me on stage.
One month ago, in Iceland, we celebrated the launch of our Mammoth plant, which is the worldwide largest direct air capture and storage facility, and which at the same time was a 10x scale-up of our Orca plant that is in operation since 2021 and delivering CDR to our customers. Everything that we have embedded in those two plants and all commercial plants that we've built so far dates back to about 1.5 decades ago when we started Climeworks from a small laboratory reactor at ETH Zurich. If we look at the technology that is employed there, there is a lot of facets, a lot to look in. Let's zoom a little bit into the Mammoth plant. If we look in there, there is one very crucial element that is essential for all direct air capture technology. It is the way how you contact the airflow with the filter material that you're using, or the filter medium, I should say, that you're using. And since you need to filter a lot of air, it is crucial how you design that. If you zoom a bit further in, and yet a bit further, you will figure out that over the years we have designed a filter structure, we have designed a mechanism made out of flow channels where the air goes through, made out of channels where the sorbent, our filter material, is contained, to contact both as efficient as possible and to take as much CO2 as possible out of the air per every module that we are building. That has been quite optimized, quite developed over time, and it's quite efficient, but as we will see in a minute, this is not the end. Both the Orca plant and the Mammoth plant and all of our commercial installations, they have delivered over the past years. We're looking back to 3 years of carbon dioxide removal delivery to our customers. We're looking back to 120,000 hours of operational experience in direct air capture. All of this data going into the optimization and the further learnings to further develop our technology. And we're looking back to 7 years of field experience with our plants. Looking forward, they also will deliver. As they are already doing today, very big number, 200 million data points measured in our operational plants worldwide every day, which go, again, into the further development and optimization of our technology. And over the next years to come, our plants will deliver the currently only worldwide independent third-party certified direct air capture and storage product. Now, all of that is dating back, or the basis of that has been laid over more than a decade of both development, technology development, but also deployment and learning. We've built a total of 3 first-of-its-kind plants. If you look at that time scale, every 4 years, we have scaled up our capacity by a factor of 5 to 10, roughly. We've deployed about 250 million capital in our commercial field infrastructure in commercial operation. And every day, we've learned from the field, we've learned from our operations, and taken that into our technology. For those of you who haven't seen that, I can highly recommend our article we've recently published about the learnings of field deployment of direct air capture. All this together, which builds the basis of all the plants we've built up until today, that is what we refer to as our Generation 1 and Generation 2 technology. What many people don't know, that a lot has happened in the background in the meantime. Over the past 5 years, we've been working on what is next. Today at Climeworks, we are 500 people. 180 of them are working in R&D, in research and development. And a large portion of them, over the past 5 years, have been diving into what comes next. What can we do to always be at least one step ahead of what is out there in the field? What are we doing already out there in the field? And they've been working on what we call Generation 3 Climeworks direct air capture technology. Today is the day where we're happy to tell about it and give you a bit more insights of what we have come up with as a result of that big development program. Looking back one step, what were our goals? It was actually a quite simple set of goals that we set ourselves when looking at what do we have out there in the field and what do we need tomorrow to succeed. First, it is about the increase of our capacity. The engineers also call that throughput. How can we make sure that we can get as much CO2 out of the air per year, per unit module as possible? The other factor that we wanted to increase is the lifetime of our filters. When implementing direct air capture, no matter which technology you use, you're always dealing with some matter that interacts with the CO2. And typically, that matter does not have an infinitely long lifetime. So if you can increase the lifetime, you'll correspondingly decrease your costs. And thirdly, which might be the most important factor on the slide, is energy consumption. So a lot was targeted on how can we reduce the amount of kilowatt hours needed per ton of CO2 that we remove from the atmosphere. How can we reduce our energy consumption? And putting all of that together, we look, of course, at substantially reducing our costs at the overall goal as the overall goal to be achieved. Now, in order to do that, we had to unwrap quite a bit. We unwrapped all the elements of our technology. We looked into the sorbent materials, into the chemistry, into those chemical molecules that are interacting with the CO2. We looked into how can we structure these materials? How can we design new contactor structures? Getting back to what I said in the beginning when zooming into our Mammoth and Orca plants. We looked into our process. How can we drive the adsorption and desorption process over our material in order to reduce energy consumption, to reduce time, to squeeze the maximum of CO2 out of it? And of course, we also did look into the design. Design meaning, on the one hand, our modules, the containers, the collectors that take the CO2 out of the air, but then also the overall plant design. How can we make that as efficient as possible? Before we share more details, let's step back for a moment and let's have a look at what the team came up with.
Since 2009, Climeworks has one mission: to build the technology that fights climate change. Today, we're thrilled to announce that we push the boundaries even further. This is Climeworks' third generation of direct air capture technology. 100% more CO2 captured, 50% less energy usage, and 50% less cost. This is the third generation of a technology designed to reclaim control of our climate future, to protect our home, and to lead the race to zero.
So as you could see, quite a bit will change in our future plans. And again, we unwrapped a lot of the elements. And we want to show you a little bit more of the details, a little bit more of what we've done. And one crucial element, again, is at the heart of each of the Climeworks plans. It's about the filter structures, the contactor structures that take the CO2 out of the air. When looking at that, we asked ourselves, how can we increase speed? How can we make things faster? The chemical engineers refer to this as the so-called adsorption kinetics. The kinetics is, again, the chemical word for speed. So we asked ourselves, how can we achieve that the CO2 is adsorbed in a much faster way? And even thinking one step further, how can we remove the CO2 from our filters, again, much faster? Because if we could do that, we could achieve one of our main goals, increasing the throughput, making more CO2 capture per day, per year possible per every module we build. And to look more into this and to showcase a little bit what we've done there, I would like to invite Maxime Tournier on stage, who is our VP of R&D programs and who's prepared something to showcase our improvements and to show you the potential of what we have developed over there. Maxime.
Thank you, Jan. So indeed, at the core of our Gen 3 technology is a new sorbent material. A material that not only lasts longer, but it captures CO2 way faster. But we wanted to show it to you to make it concrete. So we've come up with a little experiment that we ran in our lab a couple of days ago. This is a simple 1 meter cube airtight box. Within it, we've placed two things: a CO2 sensor that measures the amount of carbon dioxide in the atmosphere. If you were to put it outside, it would read roughly 420 ppm. Here in this room, probably a little higher, because all of us are breathing heavily in excitement of the day ahead. And the second thing is a little fan, in front of which we've put a new sorbent material. And we run two experiments. In the first experiment, we've put a sorbent material that we use in Mammoth. In the second experiment, we've put a new Gen 3 material. And then we turn the fan on. In essence, this is direct air capture at microscale. It's about removing the excess carbon dioxide that's around us. And what we see, the results show us, is that our Gen 3 technology is cleaning up the atmosphere within that box from carbon dioxide in half the time. And it's not doing so by working harder. The same little fan, the same amount of material, we just do the job in half the time. And this is super exciting, not only for me, not only for the tens of engineers, researchers, scientists, designers that have made that breakthrough possible, but for all of us in this room. Because this is paving the way to Climeworks direct air capture at megaton scale.
Now, this is one element that is at the core of every plant, the core of every module. The other element we unwrapped heavily was on the design side. You've seen already a first glimpse in the video that our plants would look differently. We rethought how we could modularize our plant. Modularization is and will stay at the core of our technology strategy. By building plants in a modular way, we can keep up at what we've been really good at Climeworks in the past, and that is, again, speed. In this case, not speed of adsorption, but speed of development. By making modular plants, we could have come up with a new design, with an iterated design, with a facelift, or as today with a new generation every 3 to 4 years instead of every 5 to 10 years, as it is the case in many conventional industries. So we rethought modularity, and we came up with what will be the new building block of future Climeworks plants, what we refer to as a cube design. You've seen it in the video, but we've also brought it to you here in 3D. This is not the real size, otherwise it would be something like 23 meters high, but it still should be quite tangible to see what that means. And to look a bit closer on that, I would like to invite Kyle Allen on stage, who's our Senior Manager for System Integration and Validation, and he'll help me to unwrap. At the top, but that's fine. So Kyle basically has spent the past 2.5 years in putting all the different elements that all our specialists, our experts have put together on the side of material, on the side of contactor structures, on the process side, on the design side, putting that all together, integrating that into an overall system design, and then looking at that and beating at it, trying to think what could go wrong and trying to de-risk it. So let's listen to Kyle what this is about.
Thanks, Jan. Today, ladies and gentlemen, it's my distinct pleasure and privilege to be able to introduce you to Climeworks' new Gen 3 capture unit, which we've appropriately dubbed as the Cube. The Cube is a paradigm shift in the way that Climeworks' modular technology is implemented in the field. A steel structure starts to be able to support our 16 container assemblies, which are spread equally across the 4 distinct sides. Each container assembly is designed with thermal efficiency in mind. Rather than having multiple process chambers within each container assembly, this has been reimagined such that each container itself is a single process chamber. A pair of doors moves between each container assembly vertically to allow for the execution of the CO2 desorption process. As far as adsorption efficiency goes, we've managed to add a centralized fan array on top of the cube to help to homogenize the airflow through the 4 walls of the cube, through our adsorbent material, as well as to redirect the decarbonized air coming from our process up through the fans, which will be better put together on the real thing than this model, up and away from the cube into the prevailing winds, preventing that decarbonized air from re-entering our process and thus increasing our process efficiency. The cube itself is surrounded by wind and weather protection to help safeguard our Gen 3 adsorbent material from even the harshest environmental conditions. The cube design is inherently stable, utilizing one of nature's strongest shapes for enhanced structural stability, which is perfect for potential worldwide deployment. Each cube extracts from the air the equivalent amount of CO2 as 1 elephant's worth from every couple hours of system operation. This design vastly decreases Climeworks' overall resource footprint for carbon capture, decreasing land and energy use, all while increasing overall system reliability. We are excitedly preparing for deployment of this capture unit in Project Cypress in the United States and in other projects beyond. Thank you. And now, Jan will give you an overview on how we're validating this technology out in the field in large scale.
Thank you, Kyle. Thank you very much. Well, I think we would all agree that we maybe have saved the best part for the end, or as the last one. Now, everything that you've heard so far, that is not theory, and that is not only models, that is not only design, and that is not only laboratory scale experiments, but it is real and it is full scale. In order to look into the validation, about a year ago from today, we have rented a new plot in Basel, about an hour from here. So this is our latest Climeworks facility that we have in operation, with the plan to do two things. You see what we planned here a year ago. On the lower left-hand side, that is a demonstration unit for one full-scale container containing our third-generation sorbent structures, processes, and design, and everything that belongs to that, with the aim of validating the full performance at full scale in the field. You see those long air pipes there, just to name one example. Those are there to measure the airflow, because when you take CO2 out of the air, you have to move a lot of air, and actually measuring the amount that you're moving to calculate how much you have extracted is quite a tricky challenge to solve. So this one is particularly designed for that. And on the other hand, on the upper right-hand side, you see a full cube to be built as a prototype, as a basis for all future plans to be built. Now, while the cube is still in the making, I need to commend the team for the other one. Because over the past year, we've, in record speed, made it possible to design and build such one full-scale container collector filled with Generation 3. About 3 weeks ago, we had the ribbon cutting of that one in Basel, which you see there on the left-hand side. This is how it looks today. You see the air exhaust in the middle down there. You see the air intake in the top. And this plant has been now in test operation since 2 weeks. And something happened that has never happened in the history of Climeworks. Normally, when you build these plants, you start them and they don't work. You start them and they show something which doesn't make sense. You start them and you operate them, you fix the first bugs, and you measure something which you have not expected. And you measure something that you need to explain, and you need to work months and sometimes years to make it happen. It feels too that the team somehow knew that this time we had a hard deadline, which is today, and we actually made it work much, much faster than ever in the past. Within 2 weeks, we were able to collect measurement data, which not only made sense, but they also are quite consistent with everything that we've modeled today. And thirdly, in some aspects, they even exceed our expectations. If we put that into numbers, with the data that we've extracted from this first full-scale validation of Climeworks Generation 3 DAC technology, we were able to show that indeed we can increase the throughput, we can increase the amount of CO2 that one container collector can take out of the air every year by at least a factor of 2, so a plus of 100%. We can continue with our predictions that the sorbent materials will be able to last 3 times longer. That's the parameter that we still have to prove once things are really deployed in the field, but we've not seen anything that speaks against our models here. And maybe most importantly, with the first measurements, we were able to reduce energy consumption by more than 50%. It looks like we have even some more potential, but that'll require a few more weeks and months to go. If we put all that together, these results will allow us to reduce the costs of taking CO2 out of the air by at least 50%. This will be the basis for what we've seen before in the video for our next big deployment that is foreseen for 2027 in Louisiana in the United States. And more importantly, these results build the basis of the next step on our cost reduction curve. Many of you are well known, have made a long way through this domain, have talked to many players in this field, and you will have seen many, many cost reduction curves. Many of these curves are based on ambitions, are based on projections, are based on ideas, are based on hope. What we have shown you is a curve that is based on facts, on measured data, at full scale, at reality. What we've accomplished so far builds the solid foundation for the next step on this curve that Christoph has shown you, and then for the further optimization towards our 2030 and eventually 2050 goals. And I would like to take that opportunity to say a big thank you to the overall team. And what we've actually done today, we've invited the core team that has been working on this new generation over the past months and years, and I would like to invite them on stage so you can see the faces behind those developments. Thank you for that. So those are really the ones who deserve the real applause. Some of you have been working on this just for a couple of months. Some of you have been working on this for 5 years. And all of you have worked on different areas. Some have worked on the details of the chemistry of the sorbent material. Others have worked on the structures of our contactors. Others have worked on the process. Others have tried to crack the energy equations and try to take every single kilowatt hour out of our process. Some have worked on the design of the contactor, of elements in here, others on the whole plant design. But all of them have been united by the idea and by the strong conviction that we can make the next big leap in direct air capture technology possible. And I want to thank you for that. Thank you. So all what we've talked about so far, what I've explained to you and what I've shown you, those are the factors that I'd say we can influence. Sometimes it's a bit harder, sometimes it's easier, but that is technology, that is development. We can invest more in people, we can invest more in infrastructure. We can do something about that, and it's quite well under our control. If we now think about the next step ahead, if we think about scaling it up to millions of tons, to tens and hundreds and eventually billions of tons, that is something that we can't do alone anymore. This is something that we have to do together and where we need the contribution of all of you. There are a few elements that we absolutely do need. We do need offtake. We need corporates who incorporate such type of technology into their net zero negative strategies. We do need policy. We need eventually public procurement. We need mechanisms that enable the scale up to billions of tons from millions of tons. And we do need investment. We need substantial investments in large-scale infrastructure, such as this one over here. And if we work all together on this, this brings us to the fifth ingredient. Christoph has shown the 5 ones in the beginning, the 5 success factors of market readiness. If we all work together, we can achieve something like other industries have shown. Let's work on making direct air capture the next solar. Solar PV has outperformed any predictions and any hopes to that technology. If we look at the installed solar capacity in the year of 2020, that was 20 times higher than the predictions in 25, and that was 125 times higher than the predictions were back in 2000. And we can do the same for this industry. If you are interested in being a part of that and you feel that direct air capture is one element, but there should be other elements added, I can just comment to that thought and totally agree to that. Based on our experiences on the market, on the needs, what does it take to make carbon dioxide removal as a whole a reality? Two months ago, we have launched what we call Climeworks Solutions. So as of today, Climeworks is not only providing direct air capture-based carbon dioxide removal based on our technology, but also a portfolio of other solutions based on other technologies, approaches, nature-based solutions, such as afforestation, such as biochar, or enhanced weathering. And this is something we can offer to all of you. We are happy to discuss, and we'll also learn about that more later. Now, in the very beginning, we've listened to one chapter, one excerpt of the book, The Ministry for the Future. There was a pretty depressing one, or a one which we really don't want to take that road down towards that scenario. So maybe there are other ones. And to end this, let's listen to another chapter.
Everyone knows me, but no one can tell me. No one knows me, even though everyone has heard my name. Everyone talking together makes something that seems like me, but is not me. Everyone doing things in the world makes me. I am blood in the streets, the catastrophe you can never forget. I am the tide running under the world that no one sees or feels. I happen in the present, but am told only in the future, and then they think they speak of the past, but really, they are always speaking about the present. I do not exist, and yet I am everything. You know what I am. I am history. Now make me good.
Now make me good. Well, Christoph spoke in the beginning about leading the race together. And I want to invite you for something. If you have looked carefully at our shoes, you might have spotted something. You've seen our laces look a bit different than they would normally look. And, well, in planes, they used to say, please find your life vests under your seat. I would like to invite you to look under your seat or the seat in front of you. You will find one pair of these Leading the Race Climeworks laces. And I would like to invite all of you to take them out, put them on for the day, and join us in our race towards net zero.